Hello and welcome to Physics Frontiers. This is episode number 63, Gleason's Theorem with Blake C. Stacey. Blake is a mathematical physicist at the University of Massachusetts, Boston, where he's a research professor in the Cubism group. What brought Blake to my attention was a brief article in the archive on two recent approaches to the Bourne rule, where he looked at basically two different papers that were trying to in some way replace the Bourne rule. The essence of his discussion was that the things they were doing were very similar to Gleason's theorem, which is a foundational theorem, the mathematics of quantum mechanics, in the most mathematical sense of the word mathematics. And Blake and I had a really great discussion about that paper. It lasted about 2 hours. In fact, the first 45 minutes or so were about Gleason's theorem itself, and not about the other two papers. Gleason's theorem is something that's a very interesting topic, and it's something that I would like to share with you. So what I've done is I've split this, and so I've split that discussion into two parts. So this will be the Gleason's theorem episode, and then next time we'll talk about replacing the Bourne rule, why you'd like to do that, and so forth. But to really understand some of that, we want to talk about Gleason's theorem first. So the papers that Blake and I discussed were Andrew Gleason's original paper from 1957, Measures on the Closed Subspaces of a Hilbert Space, and then two more recent papers. One that provided a similar proof, Quantum States and Generalized Observables, a Simple Proof of Gleason's Theorem by Bush, and one that extends it in an interesting way with quantum information theory, and that was Gleason-type derivations of the quantum probability rule for generalized measurements by Caves, Fuchs, Mann, and Rennes. I think we had a lively discussion here, and I hope that you will agree after you've listened to it. Show notes for this episode can be found at frontiers.physicsfm.com/63. Show notes will include all four of the papers I just mentioned, so you can read along, as well as the books that we mentioned in the conversation in this episode, which were numerous, other similar papers on the side, related episodes of Physics Frontiers, and things like that. And so here was my discussion with Blake Stacey. Today on Physics Frontiers, we're going to talk to Blake Stacey on his paper on two recent approaches to the Bourne rule. And those are two recent approaches, one by Massanes and Hassenfelder. And we're going to roam around a lot. There are a lot of places where we want to go, but I really liked this paper when I saw it on the archive on two recent approaches to the Bourne rule. And I thought it was right up Physics Frontiers alley. It was doing exactly what we like to do, which was it looked at a couple of different papers on the same topic and was talking about them in a very interesting way. So basically, I think what I saw was on these papers, you were comparing both of these approaches to Gleason's theorem. Gleason's theorem is, well, Blake Stacey is a very, very brave man. Okay, so this book, An Introduction to Hilbert Space and Quantum Logic, is a book that I reviewed on the internet earlier this year, and picked it up as an undergraduate because we had a really great college bookstore that had a big shelf full of Springer books. And right after I took functional analysis, this was the easiest book on the earth to read. And 10 years later, it was complete gibberish, right? So
that sounds about right.
But for the proof of Gleason's theorem, chapter 6 is basically leading up to the proof of Gleason's theorem in this book. And for the proof of Gleason's theorem, at the very last page on chapter 6, it says proof omitted. This is the
classic.
This is one of the most significant theorems with one of the most difficult proofs in the entire foundational scheme of orthodox quantum physics. So this is what we're going to talk about today.
Where angels fear to tread.
That's right. What I'd like to do is start off just talking about Bourne's rule, just to remind people about what that is. Talk a little bit about why there seem to be so many people who want to do something with it, and then get into Gleason's theorem and these other two papers.
That sounds like a plan. Or plan-shaped entity.
All right. So here's my cartoon of quantum physics. Generally, people like to break it up into two parts. We have this nice deterministic evolution of this thing called the wave function that comes about from the Schrodinger equation. And then every once in a while, there's some measurement that comes along. And all of a sudden, you have this irreversible event that happens. Not everybody who does quantum foundations thinks that's a great description of it, but that's the way it's normally taught. And the Bourne rule is basically taking this Schrodinger equation that's evolving this quantum state and saying, okay, well, we're going to apply some math, we'll get some probabilities, and after that, we'll find out what the state is afterwards. So that's basically the place of the Bourne rule, as far as I understand it, in quantum mechanics. This is one of these things where the Bourne rule isn't actually what they never say this is the Bourne rule in your undergraduate, or I didn't even hear it in my graduate class in quantum physics. So it's just something that shows up a little bit later. Somebody actually tells you somebody made this up at one point. At the beginning, they're just sort of saying, well, this is obviously what happens. And here's all this fun math that you get to do for the next 3 months. But, there's actually something going on behind it. And it's pretty interesting. So I think the first thing I wanted to do is see how much of that do you agree with or disagree with? Because, I thought this was fairly standard. And then maybe the third time I read your paper here, it sounded like you might have some issues with some of the way that is presented. Is that okay? It seems like there might be something I'm missing in that cartoon.
As cartoons go, I think that's a fairly good one. This is, of course, a topic where it's very easy to slide off into a fog of confusion. And I think it was aptly summarized by Don Cabello when a few years ago he made a chart of the different so-called interpretations of quantum mechanics and tried to classify them to at least a first approximation kind of way. And the title of his paper was A Map of Madness. And I found that quite fitting. And of course, you have further problems where not everyone who pioneered the subject didn't actually say the things that have been attributed to them, because physicists are very sloppy about history. So there's just complications upon complications when we talk about these things. And it's interesting to think about why that has happened in quantum mechanics so much more than anywhere else in physics. If you stack up the literature on interpretations of quantum mechanics and compare that to interpretations of special relativity, interpretations of thermodynamics. And of course, people do talk philosophically about special relativity or thermodynamics, but the general level of confusion with quantum mechanics is just vastly, vastly greater. And one of the challenges I think that has contributed to that over the past 100-ish years is with a subject like special relativity, we have Einstein's postulates. And basically, we can just spell out the theory in words. You can say a lot about the theory and what's the most important features of the theory by saying inertial observers will agree on the laws of physics. Inertial observers will agree upon the speed of light. And by inputting a little bit of math about coordinate systems and such, you can then derive all the formalism of the theory. And then when you're in the middle of a calculation in special relativity, you can always refer back to Einstein's postulates and get that qualitative check upon your reasoning and go, oh, whoops, suddenly I've broken Lorentz invariance. I've done something horribly wrong. And so we just have a better conceptual grounding of the theory upon postulates with a transparent physical meaning. Whereas, and you hinted a little at this in what you said, when we teach quantum mechanics, we kind of dump a few chapters of linear algebra and functional analysis upon the poor student and say, here, have fun.
Yeah.
And we don't do that out of cruelty, or not just out of cruelty. It's because we don't have much of a better clue. We don't have the counterpart of Einstein's postulates for special relativity or the 4 laws of thermodynamics. What are the 4 laws of quantum mechanics? Can we say them in a way that doesn't depend upon the elaborate successive levels of mathematical sophistication that we build up in the textbook development and the ordinary development of the theory? This has been a problem which has vexed people who care about such things since the early days of the subject, in some fashion or another, going back to von Neumann is generally credited as being the first to sort of thinking along these lines. Where does the math of quantum theory come from? From what list of physical and logical postulates can Hilbert space and vectors and Hamiltonians, unitary operators, the Schrödinger equation, tensor products, eigenvectors, eigenvalues, positive operator valued measures, from what list of the four laws or the analog of Einstein's postulates can all that be derived? And if we knew that, we could maybe say things like, okay, if we ever have to modify quantum mechanics for any reason, well, then we might actually know what we can change and what we have to keep. Sometimes when you talk to people doing black hole physics, they say things like, well, maybe we need to patch up quantum mechanics somehow to deal with black hole evaporation. It's not the most common sentiment in that community, but it does exist. And then you have to ask, well, how can we modify quantum mechanics in such a way that it is still internally consistent and doesn't spoil our ability to correctly predict all of the things where the predictions of quantum mechanics have already been checked out? If we're ever in the situation where we need to modify quantum theory for some reason, what are the ways in which we can do so? And it's really hard to see how one might be able to make any changes that are consistent by just going in and blindly swapping out bits of the algebra.
And then Gleason's theorem, which has a history, apparently it builds up from von Neumann. I'm not sure if it was in your paper or somebody else's paper where, they said von Neumann had an idea, then...
Right. You go back to late 20s, early 30s, von Neumann is trying to develop a mathematically rigorous formulation of what the physicists had been doing. And this is eventually codified in his Mathematical Foundations of Quantum Mechanics, originally published in German in 1935, thereabouts. Very German, very thorough, and eventually translated it in English in an edition that has that wonderful old school typewritten typesetting. But towards the end of this book, von Neumann starts talking about what are the logically consistent refinements or possible extensions or modifications of the quantum theory as he has developed it. And this kind of ties into the question of what would later be known as hidden variables. And the question by von Neumann's time, it's past decade or so, they've had the uncertainty relations, originally proposed in a kind of a bit wishy-washy way by Heisenberg, who didn't give a very exact definition of what the spread in uncertainty, what the measure of that should actually be. Then Pauli and Weil and others came along and kind of nailed down the way that is taught now, talking with the standard deviations, expectation values, and so on, till eventually we have the modern understanding of, whenever you have non-commuting Hermitian observables, you can deduce this uncertainty reciprocal relation upon expectation values. And that invites the question of, is there an underlying level with more certainty? Is that quantum uncertainty just due to our being ignorant of the little wheels and gears inside the electron? Are there gears inside the electron such that if you know which way the gears are aligned, you could predict both the outcome of a position measurement and the outcome of a momentum measurement, regardless of the uncertainty relations? And von Neumann put forth an argument that you can't. According to Eugene Wigner, von Neumann had a much more physicist-y, heuristic way of arguing that, if there were hidden variables, you could eventually winnow down to and find the value of the hidden variables. And since it appears you couldn't do that, then quantum mechanics was actually inconsistent with the idea that there are these underlying gears inside the electron. But the argument in the book is a very mathematical, formalized argument. And some people found von Neumann's argument persuasive. And here we get into kind of lots of secondhand physics history and not being entirely quite clear what people meant, and stories told from somebody who heard it from somebody who heard it from somebody. The story goes that Einstein was once in his office and the assistants or someone asked about whether there could be hidden variables underneath the quantum uncertainties, and the topic of von Neumann's supposed proof came up, and Einstein pulled von Neumann's book off his shelf and opened it and pointed to one equation in the proof and said, "Why should we believe that?"
Okay, yeah.
Einstein wasn't the only one to call von Neumann's argument against hidden variables into question. There's a philosophy of physics book from the 40s arguing that von Neumann presumed too much. If he didn't quite presume his conclusion, he at least went in with assumptions that were too strong. But very quickly after von Neumann came out with his argument, Greta Hermann came out with a paper arguing that one of von Neumann's assumptions was unmotivated. And one of the necessary assumptions to make von Neumann's no hidden variables theorem go was just unwarranted. And without that, you couldn't make von Neumann's argument against hidden variables, his formal argument against hidden variables, go. You're kind of left in this limbo where if there are hidden variables, von Neumann's argument will tell you that they have to look very different from the quantities that appear in quantum mechanics. But other than that, we can't apparently say very much. Who exactly was convinced by von Neumann, how well they understood what he was saying, that's a bit up in the air. And whether people were convinced by von Neumann's actual theorem or just the overall feeling of soundness of the way he formalized quantum mechanics. Physicists aren't always the sort to be convinced by a single theorem, because a single theorem is no better than its assumptions. But when you have a whole theory that just hangs together so well and kind of starts to feel like there's no room for anything else, the thoroughness of the axiomatization seemed to make it very hard to see where hidden variables might be coming in. And reading the late 20s to late 30s texts, the sense one gets is more that quantum mechanics would be found to be wrong in some way, be subsumed by an improved theory, rather than the way we think of it now, where quantum mechanics is very well tested and has been found to be very bulletproof. So nowadays, we ask the question, can there be a hidden variable explanation of some sort underneath quantum mechanics, which is a very well-tested theory? Whereas 1928 through 1938, people are saying, what are the ways in which quantum physics might break down at high energy, short distance scales in presence of gravity? And then after that, they come back to the question of how do you properly combine quantum mechanics with special relativity? And that's occupying people in the late 40s, starts to become successful in practice, 46, 47. So by the 50s, it's like, okay, quantum physics doesn't seem to be breaking down in practice, but we're always vexed by these arbitrary seeming nature of the overall, why are we using this mathematics rather than some other mathematics? Why do we having to talk about observers and measurements? That makes us feel kind of icky because we want to be more hard-nosed scientists than that. What qualifies a device as a measuring device rather than just an object? So in the 50s, you start to see people poking around trying to formulate approaches to answering those kind of questions. And by the mid-50s, you get George Mackey, who wrote a review article that was basically, if you're a mathematician, this is what you can take quantum mechanics to mean. He tries to do the Euclid's postulates thing or quantum mechanics. And it's like, well, we don't know where these rules came from, but this is what it seems like the rules are. He asks, does the rule for calculating probabilities given a quantum state have to be the rule that the physicists have agreed upon? Is that deducible from the other axioms? That was the question which Gleason got interested in, Andrew Gleason, and very quickly thereafter came out with Gleason's theorem, which provides an answer. The original form of Gleason's theorem went something like, if we assume that to each quantum mechanical system of interest is associated a Hilbert space, a vector space, basically. And we say that a measurement, however measurement is implemented physically, the mathematical representation of a measurement is an orthonormal basis for that vector space, where each vector in that basis corresponds to a possible outcome of the measurement. Well, the job of the theory, at the very least, has to be to tell us what the probabilities of the measurement outcomes are for each measurement we can do. That's very pragmatic. Our theory has to give us at least that. So Gleason says, okay, we'll take that to be our definition for now of what we mean by measurement as an orthonormal basis. And we want to assign a probability to each vector in each basis. We make the assumption to bind different measurements together. We make the assumption that the probability attached to a vector is independent of what basis that vector might be embedded in. If you think about three-dimensional space and you say, okay, I need to assign a probability to x hat, y hat, and z hat, but I also need to assign probabilities to all the other measurements I could do, some of which are rotations of that original set of axes that say leave z hat in place and rotate around the z-axis, so rotating in the xy plane. So I also need to assign probabilities to all those measurements. And Gleason makes an assumption of context independence, where the probability assigned to z hat is the probability assigned to z hat, regardless of what basis I happen to think of that vector as living within.
But z hat still has to be a basis in your measurement scheme, right? It still has to be a basis vector.
Right.
So there are so many different ways you can do this, but any way that you could measure z, it still has to have the same probability.
Yes.
So no matter what your experiment is, they can have different sets of orthonormal projections. That z projection always has the same probability. That's what's important here, right?
Right.
Okay.
And from this very minimal seeming set of assumptions, Gleason deduces quite a lot. He showed that any consistent assignment of probabilities to measurement outcomes, which respects those rules of measurements are orthonormal bases, mathematically speaking, and the context independence of those probabilities for basis vectors, has to take the form of, for some linear operator, the trace of the product of that linear operator with the projector onto the basis vector. You have to be able to write it as trace of operator rho times, in Dirac notation, it would be ket psi bra psi for the vector psi that you're considering. And that's any map from vectors psi to probabilities, to the unit interval that meets this condition of context independence has to take that form for some density matrix or density operator, traditionally written with a rho.
So he's really constrained the possibilities.
Really constrained the possibilities, not just giving the state space. He's not just deduced the set of density matrices. So he's not just derived that your set of possible state assignments is the set of positive semi-definite matrices with trace 1. He's deduced that, and he's deduced the rule for combining a density matrix, a description of how your system is prepared, with your description of your measurement. He's deduced that the rule for combining those is to multiply the matrices and take the trace.
Now, one thing you suggested I read was Caves, Fuchs, Mano, and Renes, Gleason type derivations of quantum probability rule for generalized measurements. Yeah, and in that paper, they spent a lot of time building up, they called them sort of fuzzy operators that were sums over these projections. I'm a little confused. How do those fit in?
Okay, so what that paper and also another paper by Paul Bush, who arrived at the same result, did was to say, okay, it's been a while since 1957 when Gleason came up with his original theorem. Some things have happened in the interim, one of which was the arrival of quantum information theory. And quantum information theory is much more concerned with tasks like transmitting messages and protecting them against errors, coding, computation, how to distinguish two messages reliably, that kind of thing, rather than the just finding quantized analogs of classical physics problems. That had been the mindset for a very long time. Quantum information theory starts taking off in the early 90s, brings with it conceptually this change of viewpoint where uncertainty relations, for example, had been thought of as like an imposition upon our abilities. We should have had the God-given right to measure position and momentum simultaneously to arbitrary accuracy, but we are frustrated in our ambitions. But quantum information theory with quantum computation came along in the early 90s and said, well, God has closed the door but opened the window. That quantum theory, while it has foreclosed upon the possibilities which you might have wanted to do, it also brings new possibilities of things which you didn't think you could do before. Potentially, if you're very clever, you can speed up computation, unlock new potentialities of material objects if you're just very clever at thinking about and manipulating them. Along with that conceptual change came something of a mathematical change, where instead of thinking about a measurement as a Hermitian operator or more or less equivalently an orthonormal basis, starting originally in the early 70s and then with increasing preeminence in the 90s, came this idea of what's called a positive operator valued measure, POVM, or generalized measurement. And the idea of a POVM is, say your quantum system to your physical system of interest associated a Hilbert space. A measurement is now any set of positive semi-definite linear operators on that Hilbert space, which sum up to give you the identity operator. And each operator in that set corresponds to a possible outcome of the measurement. And the probability of getting that outcome is found by the quantum information version of the Bourne rule, which is trace of that operator times the density operator, the Hilbert-Schmidt inner product in fancy language of the effect operator stands for the outcome of the measurement, and the density operator, which represents the preparation, background information, however so arrived about how your system was set up. And whether or not you want to take orthonormal bases, which are a subset of positive operator valued measures, or the whole set of positive operator valued measures as the definition of the mathematical representation of a measurement, something of a matter of taste. You can implement any positive operator valued measure if you have orthonormal bases and auxiliary resources. There's different schemes for realizing how to do this. But practically speaking, if you open a textbook like Nielsen and Chuang's Quantum Computation and Information textbook, or any recent reference on quantum information, in practical terms, we can regard positive operator valued measures as what we mean mathematically when we're talking about measurements. And then the question of how you want to physically implement that then becomes a question of how do you choose a particular laboratory procedure? And in practice, these people actually build quantum computers. There's only one measurement. You're measuring the Pauli Z eigenbasis. Implementing anything else is an involved procedure. So might as well, all right, we'll take the set of all procedures whose last step is a Pauli Z eigenbasis, computational basis measurements. And all the possible protocols that could culminate in that will be our set of measurements. So you can implement any POVM ultimately in that way. So kind of, some people would insist upon the old von Neumann definition of an orthonormal basis. And other people are like, why impose that restriction? You're not making anything less conceptually mysterious by demanding that vectors be orthogonal. So by taking this proper superset of measurements as what we mean by measurement mathematically, you can drastically simplify the Gleason argument. But if you say that the job of your theory is to assign probabilities to all the possible outcomes of POVMs, you make that same assumption where if the same operator occurs in multiple POVMs, you assign it the same probability. Then you can blast through an argument in a couple pages that gives you Gleason's results, where the set of all possible preparations is the set of density matrices, Hermitian operators that have non-negative eigenvalues, trace 1. And the rule for combining a preparation specification and a measurement preparation is the Hilbert-Schmidt inner product version of the Bourne rule, trace of one operator times another. And mathematically speaking, we've made a stronger assumption, thereby simplifying the proof of the theorem. Whether that's too strong an assumption is, again, a matter of taste. But if you come to the subject thinking of implementing an arbitrary POVM by quantum random walk or what have you, is not conceptually different, more demanding than implementing any other measurement that's not a Pauli sigma z eigenbasis on my quantum computer. If that's the standpoint you come from, then you're probably willing to say, okay, I'm willing to assume that POVMs are a decent notion of measurement to start with. Then by taking that and adding that context independence assumption, then there's no freedom left in your mathematical structure. You have deduced the state space, and you have deduced the Bourne rule, and you've deduced that the time evolution that doesn't get rid of any information is a unitary transformation. So you've done something a little trippy.
Yeah.
You've started with what you mean by measurement, that ooky spooky concept. And then you've gotten back to the Schrodinger equation. You've derived the Schrodinger equation as a secondary consequence of premises that have to do with measurement, specifying measurement as a conceptual primitive of some kind, and then deducing the state space. And then if you say that a time evolution that doesn't get rid of any information is a symmetry of that state space, then those are unitary rotations.
That is very interesting. So it does seem to go a little bit backwards. I mean, but that's good, right?
Yeah, it's intriguing that we can do that sort of thing.
Yeah. Do you think that's a pretty good idea about what Gleason's theorem is? Is there something else you think people ought to know before we talk about the other papers that you looked at?
Oh, just to tie things back to the talk of hidden variables,
okay,
you can use Gleason's theorem to yield a no hidden variable argument, because if you had a deterministic hidden variable theory, for simplicity's sake, then probabilities would always have to boil down to 0 or 1. You know, the value of the hidden variable, you say what's mandatory, what's impossible, and everything's either mandatory or impossible. Pick this measurement, that will be the outcome. But there's no density operator which can give you those kind of probabilities.
And therefore,
but because everything has to come down to applying the Bourne rule to some density operator, there is no hidden variable theory that can be consistent with Gleason's assumptions.
Okay, yeah. So basically, you don't get to trace out a path, right? You don't have a specific trajectory that's viable as far as all of these operators are concerned.
Yeah. Gleason's original argument, we should say, does not work if your system is what we now call a qubit, a two-level system. If your Hilbert space is two-dimensional, you can cook up counterexamples. Basically, because if you only have 2 dimensions to play with, then there's no way to generate multiple non-trivially distinct bases containing the same vector. So it's just Gleason's context independence or non-contextuality assumption. It just doesn't provide you enough of a constraint. If you know the block sphere picture of a qubit state space, you could imagine painting one hemisphere with ones and the other with zeros, and a von Neumann measurement, an orthonormal basis measurement on the block sphere is a pair of antipodal points. You can take the north pole and the south pole to be eigenvectors of the Pauli Z operator, and then other binary measurements are, other pairs of opposite points. And one of those would always be given probability 1, the other would always be given probability 0. So you could have a deterministic hidden variable assignment of probabilities that is consistent with Gleason's assumptions, because it's just not a very strong constraint when you only have 2 vectors at a time to be assigning probabilities to. If you instead assume that the set of POVMs upon a qubit is your set of possible measurements, this broader, more expansive notion, well, a POVM can have an arbitrary number of elements, regardless of the dimension of the Hilbert space upon which it is applied. It becomes a stronger constraint, and in fact, you can make the Gleason-style argument go through where Gleason's original argument couldn't, which is a bit interesting.
Oh,
a qubit interesting.
All right. Yeah, well, I mean, at least for quantum mechanics, it doesn't seem like, mathematically, it seems like it's one of those steps that at some point you have to figure out, right? If you're looking at something as far as a mathematical proof of something. But really, I think physically,
when do you only ever have one qubit in the universe? Right?
Yeah. So, I mean, even when I was thinking about something like this, I'm trying to think of a Stern-Gerlach experiment or something while I'm going along. It says that you've got at least 3 values, but still, it's easiest to think about it in the Stern-Gerlach experiment. And just because your particular argument doesn't work for n is less than 2, I know quantum mechanics works for the Stern-Gerlach experiment. So I'm not really worried that somebody's not going to find a way to do that at some point, at least personally. I mean, somebody may have been really worried about that, but
John Bell was worried about that in some form or other. In his 1964 and 1966 papers, the 1966 no hidden variables paper was written first, and much more in the tradition coming from Gleason's theorem, which was followed up on by others. Do we really need this whole continuous choice of bases to make a deduction? And one of the things Bell does is he constructs a hidden variable model for a single qubit. And it's basically taking that, paint one hemisphere with ones and the other with zeros, and then introduce some more flexibility to it. And he's very careful and conscientious. He doesn't want to draw conclusions about hidden variables that we can't actually back up with theorems we can exactly say. So there are these phenomena that you could emulate with hidden variable-based randomness. And then all these others where the hidden variables, if they exist, would have to be non-locally distributed and meet very arduous conditions. And in the views of a lot of physicists would be much more baroque than the thing they're trying to replace.
And that would be in the speakable and unspeakable?
His 64 paper was just called On the Einstein-Podolsky-Rosen Paradox.
I think that is in the speakable and unspeakable.
It's probably reprinted in speakable and unspeakable.
Yeah.
But it is also, it was published in this weird experiment of a journal that was, depending on who you ask, called Physics or Physique, Physica.
Okay. All right.
A couple of physicists wanted a journal for thought-provoking papers that would actually pay its authors.
Oh. Okay.
And they set this up as an attempt to change publishing practices. And it foundered after a few years. Before it did, it published some very significant condensed matter theory and Bell's paper in 64. And the archives of this trilingual journal, they were recently acquired by the American Physical Society, and you can read them all online. now.
Oh, excellent. Okay.
The access was opened up. So you can find Bell 64. And it's not the cleanest demonstration along those lines, and it doesn't derive the inequality which most frequently used in experiments, but it's still a very crisp and remarkably easy to follow paper for what he's talking about and for how significant it is.
Okay, excellent. I'll make sure I have some links for that for people. So now we've got Gleason's theorem, and it's told us that we're always going to have the same probability no matter what if we make a measurement of a different property. And it's given us some interesting things about evolution as well. Or was that completely a result of the Caves, Fuchs, Mann, and René's paper?
So Gleason's original argument will, for any Hilbert space dimension 3 or more, give you a state space. And then if you then assume that uninterrupted time evolutions are symmetries of that state space, well, then you can just, the symmetries of the state space are unitary or potentially anti-unitary. By Wigner's theorem, the unitary or potentially anti-unitary maps, and the anti-unitaries look kind of weird and pathological because they're not directly connected to the identity. You can work your way back to the Schrödinger equation by saying, okay, these uninterrupted time evolutions of isolated systems are symmetries. Symmetries are unitaries. Continuous evolution over time will be represented by a continuous family of symmetries. So such a continuous one-parameter family has to have a generator, and that generator would be a Hamiltonian.
But what I'm trying to get at is when we move on to look at your paper and how these other two papers more or less do the same thing as Gleason's theorem, what is the kernel that we want to look at from that discussion?
A couple other papers from the past couple years are taking different perspectives on the jewel that is quantum theory, looking from different angles, and also asking, can we take some pieces out and regenerate them from the axioms left behind? So Gleason took out the specification of the state space and the rule for calculating probabilities given an element of state space and a representation of a measurement, and showed that you could derive those from a context independence assumption and your other axioms. Then there are other pieces that you consider taking away, and there are other ways you could think about imposing conditions on what measurements should satisfy. So the first of the two papers I was talking about, Massanes et al., was eventually published in Nature Communications.
I don't recall.
I saw it in the archive, and the nice thing about the archive is it's there to be read. And usually when a multi-author paper gets as far as the archive, the math in it is probably right or close to right. And then the question becomes, are the assumptions reasonable, and are the conclusions drawn from the math reasonable? It's usually when people who have a record of publishing things get so far as putting a new thing on the archive, they've checked enough that mistakes won't be in obvious places.
And that was my discussion with Blake Stacey about Gleason's theorem. I cut this one short because otherwise it would have been a very, very long episode. This was a very natural place to switch between the two episodes. So I would like to thank Blake here for coming on Physics Frontiers and talking with me. We'll get to do it again next time. Next episode will come out in about 2 or 3 weeks. I'll get it out a little bit faster than usual. You have been listening to Physics Frontiers. This was episode number 63, Gleason's Theorem. Show notes for this episode can be found at frontiers.physicsfm.com/63. Show notes will include the papers we read for this podcast, as well as any other papers we mentioned, as well as books we mentioned, as well as related episodes of Physics Frontiers. Thank you very much for listening, and I'll see you in a couple of weeks. Bye now.